today the 4th, right?
Yep.
Has two carbons attached to each other, and each carbon has three hydrogens on the outside of it, called ethane. So what I'm doing is I'm increasing the number of carbons each time, and just, filling out the octet with pipe. Two carbons.
You have to remember this.
Is it on the test?
Hmm?
Is it on the test?
Most likely. Since he's doing this. So I'm just going to write it all in.
You guys kind of see a pattern in the names yet?
Sort of.
They all end
Yeah,
in
A and
A.
A and E, right? That's pretty much it. The ending, A and E, it ends up, what that means is that there's all what we call single bonds. There's no double bonds. Actually, I'll talk about double bonds later. But all single bonds. So, and the prefix, the F, the pro, that tells you how many carbons there are in that compound. When we get to 4 carbons, there's more than one way to attach them. We're only going to talk about the simplest way, straight chain. Called butane. A and E, these are all single bonds. Bute tells you there's 4 carbons. Right? So we're not going to name what we call branched organic compounds. We're only doing a straight chain. We're only doing the first 10. It's pretty much straight memorization. But just so that you see where you can go with this, once we get to 4 carbons, we might arrange them, say, like this. You guys see how it still has 4 carbons, and that still has, 10 hydrogens. So it's the same formula, but it's a different order of attachment. That's a different molecule, has different properties, different melting points, different boiling point, different stuff. You don't really need to know this, but this is called a structural isomer of butane. And so we're not going to name that. All, like I said, just straight chain. Yes, good.
I'm just curious as to how you could get from point A to point B. So,
well, you don't necessarily go from point A to point B. You make this. There's a different path maybe to make this. You don't have to. We have organic chemists have all kinds of tricks. We probably could go from A to B.
but would those have the same chemical formula?
Right.
So, that's just what I'm confused about.
Well, enlighten me, because I'm not sure what you're confused.
You'll have the same chemical formula for them, but how do you know the difference between them?
How do you know the difference? You mean just by looking at the formula?
Well, between, I kind of see what you get it from the straight chain to the, I guess, pyramid.
Right, so let's say you just
How would you know the difference?
Let's say you have that formula in a chemical
Oh, you have C4H10, and that's
Right.
all you have?
Correct.
That doesn't give you enough information to distinguish between the two. You have to either be given structure like this,
Yes.
or you can be given the name, right?
Okay.
You call it you could call this 2-methylpropane. That's one way of naming it. Isobutane is another way of calling it. Different. And so once you know the name, you know that's what it is. In real life, I mean, if you didn't know the name or the structure, do an experiment and figure it out. Five carbons, straight chain, or pentane. Sometimes for butane, you'll see it called N-butane, N-pentane, and N just clarifies that it's the straight chain, it's not a branch form. Hexane's the next one. There's another pattern here, let me see if you guys see it.
Oh yeah, I see it. It's in order from 1 through 6.
Those are the formulas for these alkanes, they're called. Do you see a pattern? What's the pattern?
Every time carbon raises 1, hydrogen raises 2.
Pretty much, yeah. Or the other way of saying that is if N is the number of carbons, 2N, 2 is the number of hydrogens. This only works for alkanes. Alkanes is the general name for the class of organic compounds that only have single bonds in them. Is that okay with everybody? Let's finish that. Actually, I want to show you one other shortcut, because nobody ever recognizes this. Use what are called line drawings a lot in organic chemistry. And have I shown you this before? No? I don't think so. The line drawing is pretty much lines, right? And every time, every end of a line or every angle represents a carbon. And knowing that carbon in organic compounds will always have 4 bonds to it, any bonds that aren't taken up by other carbons are taken up by hydrogens. Those are implied. So that's that end there. That's the carbon, and this carbon is only attached to one other thing, to this carbon right here. So that means it has to have how many hydrogens? 3, right? So that's this carbon right here. You guys see how that works? The middle carbon here, this has 2 other carbons attached to it, so it has how many hydrogens? 2. Right? You see that? And this one has 3. So
The lines represent
this is propane,
and then
butane,
the fact that
pentane.
there's nothing. Actually, there's 3 in the middle, and there's 2 in the middle.
Is that okay? You guys see how that works? The hexane,
That's 3 carbons.
So the point, so the points are
The carbon.
carbon. Oh, okay. So the,
yes.
See, propane has 3 carbons on it, right?
Yeah.
And
propane.
knowing that each carbon has to have 4 bonds to
Butane,
it.
butane.
4, so 1, 2, 3.
Any bonds that aren't
Get it?
shown here
Got
are
it. Now I got it.
hydrogens.
Pretty simple.
Yeah.
There you go.
So the next one,
At the ends.
heptane.
Well,
So how did you oh. Explain, Kumar.
Hmm?
Explain
Explain what?
that.
Okay, so every dot.
What dot?
See, these are lines, right? And the lines represent bonds of carbon.
Mm-hmm.
On each bond of carbon, there's always hydrogens.
2 of them? Or?
Yeah, and since he said that they don't draw out the hydrogens, and so it's invisible to like the line drawing just represents carbons.
Okay.
And you know for a fact, if it's in the end, it's gonna have 3, right?
Yep.
Every carbon on the end has 3 hydrogen. Okay, so every carbon in the middle has
Okay,
2.
catch that?
hydrogen molecules.
So let me ask you this.
You get it?
Without
You have to explain it
counting
later.
up individually, without writing it all out, can you tell me what the formula for decking is? If you can, tell me.
Where did carbon 10, 8, 12, 22,
Very good, right? Decking, well, you know that, it's 10, but you can count up these and you get 10, right? 10 carbons, which means that there's 2 times 10 is 20 plus 2 is 100. Easy as that. It doesn't mean that C10, every time a molecule has a formula C10H22, it doesn't mean that it's decking, right? It could be some other structural isomer, there's other possibilities. Right? But this is the other way though is true. This is the formula for decking. Decking has its formula. Well, organic chemistry isn't just carbons and hydrogens. That's sort of the backbone, the skeleton of it. And then we add what are called functional groups to the carbons to create the functionality of the compound. And all I'm going to do is I'm going to show you there's more than these, the 4 functional groups they have in your book. And just, you have to recognize them. You don't have to name an organic compound here, not with the functional group are. I'll give you an example. So yeah, alcohols.
Octane fuel tanks. Come on.
I'll show you.
Okay.
Why isn't it recording?
OH group.
Yes.
Oxygen group.
10. 10C. Yeah.
It's an alcohol.
Like a decacarbon. Has 10 sides.
Hey, we learned this in biology.
Yeah.
The functional.
Functional groups, yeah.
My favorite one right
Functional groups?
Alcohol.
Hydroxide, my friend. Take that. It's a hydroxide.
I'll just go look at that capology for this thing.
Well,
Nah.
more importantly,
It's the aldehyde.
more importantly, the
Yeah.
Ethanol.
This was in biology. This was
Yeah.
in biology book. Go look at that, the functional group.
I'm not going to put them yet. Okay.
Carboxyl. Carboxyl just.
Carboxyl, carbonyl, sulfide, amino.
That's a carbonyl right there. Look at that. Okay, that's actually
That's carboxyl, yo.
I didn't see, he was covering the OH for me, so.
I see it. Where's OH at?
Maybe,
Oh, right there. I see it now.
yeah, he was covering OH for me, so it looked like.
I couldn't see OH because I was looking on here to the screen. So explain the lines again right now to me.
Okay, so every dot or every line, the line represents bond between carbons, and every end, every point is carbon molecules.
You mean
And
from, so it'd be 1, 2, 3, 4, 5, 6, 7, 8,
So
9.
these are
The top one, right?
the 4 functional
Top
groups
and
that they.
the bottom, right?
the bottom one has
There's many others.
1, 2, 3,
So if
4,
you have
5.
an
5
organic
on bottom, 4 on
compound,
top.
carbon and hydrogen,
Look at the no
and
number.
attached to those carbons is an OH
The
group,
9.
then
Okay.
that would,
The no.
that functional
That's
group is an
nine. You should
alcohol,
have
and that makes that compound an alcohol. There's,
So it's
there's
C9,
ethanol,
H18.
there's ethanol, propanol,
H.
butanol,
C9,
pentanol.
H.
18,
So
right?
all alcohols make you
H20.
feel,
Why 20?
and most of them will kill you. It's only ethanol that makes you
The ends
feel.
have 3 carbons,
And
and
that's-
everything in between has 2 carbons.
Excuse me?
And
3,
that's
6.
if it's naturally produced. If it's
3,
in the lab,
6.
So it's going to be 18
Ethanol?
plus.
Yeah.
Ethanol's ethanol.
Yeah.
18 plus
Actually,
6
propanol
is
would make you
24.
blind, right?
Is that
Propanol would make you blind.
I'm gonna-
anything,
I'm
any
gonna
alcohol
have to
but
explain.
ethanol, you probably best to do, especially the smaller ones. You don't want to.
Yeah, when you get into distilling.
So ethanol is ethanol. And now, in the lab, in our labs, and in most student labs, we don't have pure ethanol for you guys to use usually because, you got some drinking.
You want to bring some?
We spice it with methanol or something else
Oh,
to make it,
damn.
Okay, that's what I was thinking.
yeah,
Trying to
Like
spike
rubbing
the
alcohol, they
drink.
do that too.
isopropyl.
You would do that.
Huh?
Isopropyl.
Well, they add more to it to make it so it's not drinkable. I read that. I don't know if that's true or not, but that's what I read.
Cheaters.
The aldehyde, is that like the basic part of formaldehyde?
Yes, it is. Formaldehyde is the simplest aldehyde. It's
There we go.
over here.
Hydroxide.
You put a hydrogen here, that's formaldehyde.
So how does that work? So let's say you have ethanol, right? What hydrogen is replaced? Does it matter?
Not in ethanol, because all these are identical.
Okay.
So it doesn't matter. Now, in propanol, there are 2 different propanol compounds. One is one propanol with either one of these 6 replaced by the OH, or it's different if one of these 2 are replaced. These are different from these 6.
Okay, so, but the intent is you'll be removing one of the hydrogens and adding a group, correct?
See?
The intent is that you'll be removing a hydrogen and adding in a group?
Effectively, yes.
Okay.
Usually, that's not what you do. That's too hard to do. You start with a different compound.
Oh,
and
okay, I get it now.
You can add OH and you end up
How to read it?
What?
I get how to read it now.
Okay.
or
We'll just read this right here. This would be
I mean,
perfect.
structurally, visually.
Yeah. So effectively, that's what you end up with.
Yeah, that's what I just
You
did.
guys okay? Following that? If you had the
I didn't understand what you
double bond O has to have an H on one side, and
Oh, okay.
any other carbon or if
I was
it's just
trying to
hydrogen,
explain
that's
for like an hour about that. He wasn't getting it.
That's
So he finally
aldehyde.
understood himself.
If you have
Good job.
carbon double bonded to an oxygen and an OH on the same carbon attached to carbons, carboxylic acid,
Yeah, that's
and
exactly how
nitrogen, two nitrogen.
Yeah. That's precisely what he's saying. The
So
line
that's all you
is-
have to do is recognize the functions.
Dude, this is so
Oh,
easy.
yeah.
For some reason.
That's a long term. Yeah. Yeah. Here, you know what?
How bad you are.
Let's just write it this way. Okay, same thing.
Whole back sore.
Okay.
So these are ones we just have to recognize?
Yes. So all I'm asking of you is that you be able to
Let's give you
name
another
the
test.
first 10 straight chain
You
alkanes.
think everything's gonna be on this?
Those recognize the
So that's right
4
now.
functional groups. You know what? It just doesn't make sense not to have this 5th one on here.
Oh, yes. 15.
Does it have what?
He's gonna give us a 5th one. Sulfhydryl.
The ketone, if you have the C double bond O, and instead of
Ketone.
having a hydrogen on one side, you have a carbon on
Ketones
either
are-
side, and that becomes a ketone rather than,
It's in the carboxyl group.
Carboxyl has to be in the middle to be a ketone.
Yep.
what's that?
Carboxyl or
Some carbons doesn't matter.
carbonyl.
Yeah, on both sides. Do you guys see the difference between a ketone and an aldehyde?
Yeah.
Yes.
So there you go. That's your organic nomenclature for ketone.
Ketone?
I can't see.
There's too much memorization.
Too much memorization.
Next, we're now on section 5.8, molecular and formula masses, and then
Don't you dare to
whatever
erase that.
chemistry you had before, you really should have seen this, okay, but I am definitely going to go over it again, hopefully
You're
refresh
in
your memories.
chemistry today.
I'll remember this, great, okay, just sit back and enjoy.
You definitely saw that.
Wait!
Ah.
Come on now.
What? Wait on what? Okay. Did you get the carboxylic acid?
Come on, Gundam style.
I actually heard on the radio. I was pretty amazed.
He looks like the Mexican version of the Gundam style guy.
Who?
Adam. Doesn't he? I could imagine him in a suit dancing randomly.
Dude, I heard on the radio. I was pretty amazed to hear that song on the radio.
That sounds bad. I like that.
I was like, you're listening to a song you don't understand.
It's on my MP3 like to walk right now. Sorry.
You listen to a song that you don't, like, 25% you'll understand. Sexy
Exactly.
ladies. And the other one's like, what the hell is he saying?
I don't know what you're saying. I don't know what you're talking about.
Well, it sounds cool.
It's very catchy. The words that are coming out of your mouth. It's catchy. And I like it.
It's catchy and it sounds cool.
It makes me feel so Asian.
Ooh, molecular orbital. Finally.
Look at that's formula mass.
That's easy still.
Till you see it.
Real quickly,
Dude, I was
I
going
want
in
to
this
make sure
section.
that you guys are clear on this distinction. It may sound just like vocabulary, but it's really, they mean different things. We talk about a molecule and a formula unit. There's a difference. Okay? A molecule talks about a molecular compound. It's all covalent bonds. We're all non-metal. Okay? Whereas a formula unit is talking about an ionic compound. Right? And in a molecule, a molecular compound, the smallest unit of that, and it can exist all by itself, is whatever the formula, the molecular formula is. With an ionic compound, the formula unit is just the smallest whole number ratio of the elements that make up that ionic compound. In the compound, if you can see the atoms, right? So, I mean, something fairly simple with sodium chloride. It would be a sodium cation, and surrounding it, there would be a certain number of chloride ions. And then there would be sodium ions between those two. So it's not like there's just one unit of NaCl. It's a whole structure, the crystalline structure. And all we're doing when we're writing the formula, the formula unit, or the formula for the formula unit, we're given the smallest whole number ratio of each of those elements in that ionic compound. In sodium chloride, it ends up as just one sodium to one chloride, so they write NaCl. But see, the difference is, you know, when you have sodium chloride, you don't have distinct units of NaCl floating around. But in methane, that's a molecule, you have distinct units of CH4. Methane's a gas under most normal conditions. And you could see the atoms in methane gas, you would see one carbon with 4 hydrogens attached here, and then one over here, and they'd be moving around and doing whatever they're doing. But they're distinct. That makes sense? So when we're talking about molecular masses, you calculate them the same way. But we're talking about the mass of a molecule or the mass of a formula unit. That's the difference. You get the same answer numerically if you add up the masses in AMUs and grams per mole. You guys remember discussing the relationship between AMUs and grams?
1 times 661 times
Here's the
10
way I
to
remember
the
it. I already know. I mean, I already had to memorize Avogadro's number, right?
2.6?
So
Yes.
How do we write this down? Ah.
And then you.
I don't have to memorize any new numbers like 1.6 and 2.
See?
So you
If
can
you divide both sides by 6.022 times 10 to the 23rd, you get how many grams in 1 AMU. You guys see that? So that's pretty simple. I'm going to have you memorize.
I would like an example. Ten straight, see? 10 straight chain going. I'm pretty sure it's going to be on the exam.
I'm pretty sure
Let's
there's.
see. Huh?
You said everything so far is going to be on like that. Everything that came up today.
What if it is? What if it was?
What are the odds?
No, seriously, what if it was on the exam?
Oh, that's why it's so easy. And he doesn't do easy.
Yes. Alcohols, aldehydes, carboxylic acids, amines, ketones.
Seriously, what if it was?
I'd be surprised.
What is the definition of AMU? Mass of molar mass?
One atomic mass
mass
unit
unit.
is the mass, is exactly 1/12 the mass
Or one
of
mole of carbon?
one atom of carbon-12.
One atom of carbon 12?
The isotope of carbon-12.
Oh, he just confused.
One mole of that.
1/12. They chose that. They were thinking about hydrogen and other ones.
That's cool.
I have a small head, yo.
So,
Small head.
for
He has
example,
a big head. Okay, so you gotta memorize the straight chains. And this that is
Yo,
about
Lexi.
appropriate. He
You like
just
my
said
Freddy
that-
Krueger?
Freddy Krueger.
Freddy Krueger.
The gentleman had. Gentleman hat, bro.
Hey, give me my calculator.
I don't know what calculator is.
Mustard gas.
Oh yeah, I love this stuff. This is really good. This reminds me of this.
Oh my gosh. I'm about to add it all up right now.
Good luck. You need a calculator.
I know, I'm supposed to get my calculator.
Sadly, I'm gonna beat you to it. Mustard gas. Is that what that is? Damn it. It's broke.
Dude, how does he know all these numbers?
Because it's genius.
Too much of a genius. I will become that one day.
You can't become a Bell, dude.
I'll surpass them. Become a doctor that'll make, worldwide now.
He's a doctor already.
A higher level doctor.
For sure, there is no.
So, mustard gas, the formula ends up being C4H8Cl2S. And the molecular mass in AMUs would just be the number of each element in that compound multiplied by the average atomic mass of that element that you get from the periodic table. So this is the carbon, this is hydrogen, this is chlorine, that's sulfur. Before,
Expect this one to
because
be
of
the best.
the subscript 4 here, 8 here, 2 here, and 1. Gamma, 158 or so,
159,
59,
1079,
I'm nice with them.
952.
Red glass and sulfur.
No, you gotta be.
The 3 passive decimal,
You gotta
3
be.
passive decimal, 3 passive decimal, at least with this periodic table, right? But it's going to depend on what periodic table you use as to how many sig figs you allow. But, so anyway, 159.08. Which means, because 1 gram is 1 mole of AMUs, right? Right? I told you, 1 gram is Avogadro's number of AMUs. And that's not exact, that's only the 4 sig figs.
That's
1 gram is 1 mole of AMUs, and the mass of 1 mole of carbon is 12.011 grams. Just by that. Yeah. 1 gram is equal to 1 mole of AMUs. If we have 1 mole of carbon, we have 12.011
AMU.
moles of AMUs, which means we have 12.011 grams. You guys find that?
Mm-hmm.
And so what that means is the average atomic mass of the elements is also the mass of the number, the magnitude of that number is also the mass in grams of 1 mole of that element. You guys buy that?
Mm-hmm.
Which we call the molar mass. So we know not only is the average atomic mass of carbon 12.011 AMUs, but we also know now that the molar mass of carbon is 12.011 grams per mole. Which means that now that we've calculated the molecular mass of mustard gas in AMUs, we know the molar mass of mustard gas grams per mole. Yep.
So what was the formula mass again?
It's this, you work calculated the same way, but it's for an ionic compound.
Gotcha.
Or,
So does that mean 1 AMU is equal to 1 gram per mole?
no, well, 1 mole of AMUs is 1 gram. is the, really the average molecular mass of one molecule of mustard gas. This is the mass of 1 mole of mustard gas, grams. Is that? The reason it's the same is because of this.
He's writing something.
Avogadro's number is the number of anything in a mole, right? So if you have Avogadro's AMUs in 1 gram, that means we have 1 mole of AMUs in 1 gram. One gram is equal to 1 mole of atomic mass.
Come on, man.
It's not dangerous.
It's the same
Sorry.
number, but it's grams. So this is, in this one here, this formula, this is the average molecular mass of mustard gas. Because, okay, when you look at mustard gas, it has 4 carbons, 8 hydrogens, 2 chlorines, and 1 sulfur, right? And we know that carbon, for instance, has several different isotopes. There's four atoms of carbon in 1 molecule. They could all be carbon 12. One of them could be carbon 13. 3 could be carbon 12. There's different possibilities, right? And that's going to be a slightly different mass. So the overall, the mass of any individual molecule of mustard gas could very well be slightly different than this. But this is the average, just like we did with average atomic mass.
So then if we wanted to find out just the exact amount of grams per mole, we would actually need a certain value to start with.
How many moles you have.
Yeah.
So this is the mass of 1 mole of mustard gas. You know, the nice thing is, you just have to add up the numbers in the periodic table, and that gives you the molar mass of any compound whose formula is known. We use that a lot. We use that much more than we use the mass, the average mass of 1 molecule. So I don't know if you're okay with that. Really, all you have to remember is that it's the same number. All right, so now that we know that, we're going to talk about percent composition. So I did this example for you calculating a molecular mass, the molar mass of a molecule. It works exactly the same if it's an ionic compound, no difference.
Oh, okay, that was my question.
It's just that, you know, conceptually, you don't have a molecule of an ionic compound, you have a formula unit. So you have a different term for it, but it's the same way. Like, for instance, just to be sure. We have sodium chloride, that's an ionic compound. I'm just going to go straight to molar mass. Whatever that number that is, 56, whatever. So it's, you do it the same way, it's just for ionic compounds.
Are you always going to want in grams per mole?
Well, that's what it is. That's how much.
I don't like to say always.
Okay, almost always.
Okay, I'll go with that, yeah. You know, it depends, you have to read the question, right? What do you ask for?
Ooh, smart man. Smart. Oh, damn it.
For a molecule or a formula unit. We calculate the percent composition, and it's just for, what you do is you calculate what percent of that compound is taken up by each of the elements in the compound. Like in mustard gas, what percent would be carbon, what percent would be hydrogen, what percent would be chlorine, what percent would be sulfur. Now, when we say percent composition, we imply mass percent, right? Not mole percent or volume percent or something like that. It's implied. It doesn't. We don't say mass percent usually, but you should understand that that's what we mean.
Seems I won't be able to get everything done today. I won't be able to record everything today.
It's okay. Element X. This is dangerous.
General, the mass percent of any element in the compound is just how much of that element there is in the compound divided by the total mass of the compound. And you can do this for any amount of compound as long as you know how much of the element you have and how much of the compound. Usually what we do is if we're just given the formula, we say, all right, let's assume we have exactly 1 mole of the compound. And that means that the mass of the compound, the bottom, that's just going to be the molar mass, like we calculated over there for mustard gas. And the mass, the element, would just be the molar mass of the element times the number of atoms in 1 molecule.
I think it's easy to work with. Well, not in real life, anyway. In theoretical aspect. Yeah. Dang. Tell me why don't you? Yeah, did you bring something for the whole class?
Serendipitously, we've already calculated the molar mass of mustard.
Oh, I remember this. Never mind.
Do you really like mustard gas?
Like your own body.
Which part of it do you find the most fascinating? The part that it amuses people?
Amuses people. That's what I'm putting in.
That's nasty stuff. It gets in your lungs and it destroys.
That's
You
what
forgot the little
That's
pinch
what
of
the
gas.
amazing part is. I'm not nasty.
Anyway,
That's
so
when it's hard to breathe and you can't fathom what's going on.
a couple things just so you understand the way that the wordings go in these types of problems. If you're just asked for the percent composition of a compound, mustard gas or whatever, they're asking you, whoever's asking is asking you for percent of all of the elements, for carbon, hydrogen, chlorine, and sulfur. Or, probably this is the way I would ask it on an exam would be, what's the percent carbon in mustard gas? Of one of the elements. You calculate it the same way for all of those, right? If you do one, you do all. So the percent carbon would just be the mass of carbon in 1 mole,
I know, dude.
right? Because there's 4 carbons, 4 moles of carbon in 1 mole of mustard
100%
gas.
this exam.
We better get 100% on the final so I can fix my first test grade.
And the total mass of the compound in 1 mole is just the molar mass of the compound, which we've already calculated.
I don't have a calculator. Mine was going to be something about 0.4 something, 49%. 49%. I'll say 49%.
Let's go. I think it's less.
Are you making no cards already?
No. It's for biology.
I don't know. I'm talking about football.
No.
I was close enough. I was up by 10.
That's about
Damn
50%.
it.
So that 30% says 30% of the total mass of that element, of that compound is carbon.
By mass.
By mass.
And we do the same for hydrogen and sulfur. And they should add up, when you add up all the percents, it should be really close to 100. It might not be exactly 100, and that's just because of the round off from whatever period.
Oh, shit.
So smart.
For like 10 minutes. Until the next thing comes. And then you're like, what? And then 10 minutes later, oh, I remember that. And then it's said again, that's so smart.
If you
End
know,
of the pattern.
or you calculate the mass and percent composition, you can use that, you will, as a conversion factor, some dimensional analysis. And percent means per 100. So if we know that the mass percent carbon in this compound is 30.201% carbon, you can say that only for this compound, 30.201 grams of carbon is equal to 100, and 100 is exact grams of mustard.
Oh man, I love this part. When you have to use percents to figure out what compound it is.
Yeah.
Because we know that it's 30.201% carbon by mass, which means that there's 30.201 grams of carbon in 100 grams of the compound. That's what percent means 100, like, you know, say 100 cents in a dollar.
Wouldn't it be easier to just solve for all of them to get the percent mass?
100%.
Well, for every
By
it's a
right.
ratio.
You solve for all the percent element,
It
the mass
doesn't matter how
percent.
much you have, but for every 100 grams you have, you have 30.2 grams. If you only have 1 gram,
Too excited.
then you have
For the next part.
0.30.
Because now we're going to use the percents to figure out what compound it is.
Okay, is that okay? Up here, 1, 2, 3, 4, 5, 6, 6.
Get out of
4
here.
times that's 48, 6, no line, 6, 6. Here's 6, 6, 6.
Feels like
This is exact, and I just took that number.
Why do you put it as 5 sig big instead of 4?
well, because
Oh, the 4 in front. Okay, I see why. No.
no, that's the top one is 3 and the bottom one. He just did no,
Oh yeah, it's 5 sig bigs right there.
no, but yeah, 5 6 things, and he has 5 6 things.
Huh?
12.011 is 5 6 things.
Oh, I didn't see the 0 on my bed.
011. It's like 12.
I just saw that as 12.11.
Yeah.
Empirical formula. I was gold here.
You said that about like the last 10 things we did.
I was gold here. Hey, man,
This one is
I'm gonna score 100% on the next exam.
If you don't understand it,
One of the more common calculations that you have to do is to do this. You'll be given the mass percent composition of the compound and asked to figure out what something called the empirical formula is and maybe what the molecular formula is. With the empirical formula, let me tell you what they are. The empirical formula is the smallest whole number ratio of the elements in that compound. So for an ionic compound, the
I'm so
empirical
happy for
formula
this part.
is the formula. But for a molecule, it's not necessarily the same. Write some of this down.
pick it up.
Lexi.
Can you imagine? He dropped it. He's a dick.
Hey, that's on camera.
My comments are on camera.
It all is working.
Forgot about that piece.
The molecular formula for hydrogen peroxide is H2O2. The empirical formula would just be HO. What's that?
That's empirical formula because it's asking for the smallest
That was
ratio of curves.
Ho?
Just tomorrow.
No. I'm reading up there. It says ho.
No. I know exactly what you did. Poor girl.
Benzene has a molecular formula C6H6. Its empirical formula would be CH, right? acetylene would also have the empirical formula.
See.
So a lot of compounds can have the same empirical formula with different molecular formulas. They have the same empirical formulas, different molecular formulas, very different, you know, they're totally different compounds. Benzene is way different than acetylene. Benzene's a liquid at room temperature, it's, you know, it's a carcinogen. Acetylene's a gas, room temperature, is how they react with oxygen. So that's what these things are now. How to calculate this concentration.
Yay, example. Example. Does it sound like kids? Notice how your writing became harmonized to also became close.
Because I'm writing as fast as I can. Like, wait.
Look at this. Nice. All these nice and also you just get shit.
Because I have to write as fast as I
Hey,
can.
same thing with mine too. Look at this. It was going nice, nice, nice.
Then he picked up the pace.
And after that, I was like, oh, it's still nice. I was like, okay, that's still nice. Once I got to the blue, I was like,
That's not
shit.
so bad. Damn it. Damn it. Look what you did.
Don't worry, it's on computer. Do empirical formula. I'm gonna get ahead of him.
Okay, that's it. We're gonna write nice now.
No, don't write nice.
This was the easiest part because he uses Zoom 100 grams and whatever numbers there are.
What's the other number?
Hmm?
What's the other number?
It's not an example. This is how you do it.
Oh, it's not?
No.
Oh. Steps.
Yep.
Push the word. Oh, it's going on 1080, that's why.
1080.
Yeah, I was like, going on 1080 the entire time.
What's 1080?
1080p.
What the heck? What's wrong with you? I don't want HD.
That's why I was using so much space. I was like, what? I was like, why is it using so much space?
It's all about that 720, bro.
No.
It's all about that 420 or 480.
Yeah, 360. 240.
It's just a bunch of squares.
Pixels everywhere. Oh my god, that's a lot of things to write.
Exactly. I can't keep up.
I can't see, so how can I keep up?
So you've already done this actually in lab. Here it is for me.
Oh, damn.
Actually, you figured out the empirical formula not from the percent composition, but from experimental data. It's the same idea. So if you're given a mass percent composition, what you do is you assume you have exactly 100 grams, which means that, like that conversion factor I just showed you, the percent of each element is just the mass in grams of that element in 100 grams of the compound. So what you do is then you take the mass in grams of each of the element that you have, convert it to moles by dividing by the molar mass. You're going to get the moles of each element in 100 grams of the compound. Whichever one of those numbers is the smallest, divide it into all of them. And if those numbers are all less than 0.1 from a whole number, just round to the whole number. If even one of those is 0.1 or farther from a whole number, you have to multiply all of those numbers, all those ratios, by some number over itself. So as you get the number, leave within 0.1 of another number. I'll do an example. Once you do that, you have the perfect formula. Round.
What do you mean by some number over itself?
202, 3 over 3, 4 over 4, 5 over 5. Like, right, you have to figure it out, right? So say, I mean, I'll do the example, but so once you say take the moles of chlorine and divide by the moles of sulfur, right?
Gotcha.
And you get 1.5. You have to multiply that times 2 over 2 so that it's 3 over 2. Gotcha. Okay. The rest of you guys got me? Laura?
Do you do the same thing for molecular formula?
There's one more step to get to molecular formula. Oh, there's I'm going to show you 2 different ways to get to molecular formula. So I'll get to that. Right now, we just want to be able to calculate the surface. Divide those moles. Divide the smalls into. So that's the same thing. So at the bottom, the smallest is in the bottom. The other one is top.
Right, here's all. Example. What's that simple? Let's get a full.
So say you're told you have a compound,
Point
it's
8056.
composition, you're asked for the empirical formula.
Oh, snaps.
So if we step 1 assume 100 grams, that means you have 80.56 grams of carbon, 7.51 grams of hydrogen, and
What's hydrogen?
11.92.
0.00794.
Mm-hmm. Actually, it's
00794, right?
Yeah, yeah, yeah.
Let me do oxygen now.
Next, step 2, we'll calculate the moles of each. To go from grams to moles, you just divide by the molar mass. So we look up the molar masses of these elements in the periodic table.
Oh yeah. Oh yeah. Oh
So
yeah.
there is one.
Oh yeah. Oh yeah. Oh yeah. Can we turn it to decimals though? The percent.
I mean, like one oxygen.
Can we transform it to
No,
decimals?
that's the ton of carbon right there. 80% of the molecules carbon. Come on, bro.
We could see that, so we printed decimals. Like instead of 80.56, put 0.8056.
Oh, give me a second. I'm gonna do this real quick. 80.56% of carbon. 7.51% of hydrogen. And then 11.92% of oxygen. Question.
Does that make sense so far, Chris?
Yep.
So how do we know how many moles of each element we have? We just take the smallest of these, which in this case would be oxygen, divide it into everything. So you have this written down, right? I can erase it.
Oh, not all of it. You can raise them to B. I haven't finished writing B down. Oh, damn. I have to steal it. That's all I got. Where is... Ta-da.
0.745.
You know what? I'll get it down after I finish doing that equation. How's that sound? That's 15.99999, right? Oh, yeah.
Uh-huh.
Oxygen is just going to be one, obviously, right?
Oh snap. I did it wrong.
Oh, I told you, dude. I told you.
No, I got it mixed up. I switched it.
I told you.
Be quiet.
I'm joking. Don't take me seriously.
617. Oh snaps. Where am I?
7 moles of carbon. And then 7.07.
Dude, that's 19.
6 moles of hydrogen.
So C9H10O. That's like exactly 1.
4.745 moles of oxygen. So that means you can assume this of what? There's 7 hydrogens for every. You can say 8 hydrogens almost for every 1 mole of oxygen.
So in this case,
Right there.
all the numbers we got came out to be closer than 0.1 equal number. So we
19.
don't have to, yeah. So
C,
we don't have to
C,
multiply by
9,
number of
10.
itself.
C9H10A.
So what this tells us is that, okay, we divided everything by the moles of oxygen, so relative to the smallest amount of oxygen we have. For every 1 mole of oxygen, we have 9 moles of carbon, 10 moles of hydrogen, 1 mole of oxygen.
What does the empirical formula look like if I had 132 AMUs of that? What does the empirical formula look like if I had 132 AMUs
Yeah, there's something missing from that.
I figured out the empirical formula,
Oh, okay, then the molecular.
and then it's asking for the 100.
That's not gonna be next. All
I
right,
want
so
to get 10 rolls.
this is the empirical formula.
7.45
from the
divided by
mass percent composition.
0.7450.
If you're asked to find the molecular formula, the true formula, remember like in peroxide, hydrogen peroxide, that this is supposed to be like HO, right? To figure out what the actual or molecular formula is, you need to know one other piece of information.
Damn it.
You have to be given the molecular mass, molar mass.
The molecular formula. So let's continue with this.
All you do is calculate the molar mass of the empirical formula, divide it into the molar mass of the molecular formula. Round to the nearest whole number, just straight out round, and multiply each subscript by whatever that number is. So I'll write all that down.
All of them.
Yeah, what I just did. What I just said. So Adam, it sounds to me like this is what you're talking about this after. This last part. Okay. We'll see.
No, now you have to figure out what, moles dot form.
So, yeah, I'm gonna call this thing right here the empirical mass. Sometimes it'll be, after you do it, it'll be the same as the molecular mass, and that means that the empirical formula is the molecular formula. That happens.
So to find mole one, does that mean molar?
Molecular
I
formula.
mean, yeah, molecular.
Find the molecular formula from the empirical formula. You don't like my abbreviations.
So the molecular formula for this one would be that 268 grams per mole.
That'd be the molar mass, yeah. Of the molecular mass.
Oh man, this is ridiculous.
And it doesn't matter if it's AMU grams per mole, it's the same number. So Adam, it sounds like the one in South you're talking about, they give two AMUs, the same thing. So let's do this. So for this one, the empirical mass, it's just, was it C9H10O, right?
Yeah.
Now we've calculated the empirical mass, the molar mass, and the empirical formula. Given the molar mass of the molecular formula, just take that's going to be about 2. Okay, so you see what we do with this number here. This is the whole number I'm talking about here. We multiply each of the subscripts in the empirical formula by 2. We get C18, H20, by 2 for the molecular formula.
That's easy.
Of course. Until you fail at it.
What are you hating?
I'm not hating. I'm joking. Don't take me seriously.
You're mad.
I am mad. You mad, bro?
I am mad.
I'm sorry.
I'm trying to hate.
I'm not trying to hate.
I am.
Why? Damn haters. 7, grounds over moles. It's like 1 equals 2.
So from there, because I got like 0.0199, so there he just rounded up to?
Yeah.
For what? For this number here?
Yeah.
No matter what, you would always round to the nearest whole number for this. It's not like in the empirical formula calculation, where it was 0.1 or more, so the whole number we had to multiply by something. Don't do that here, just round.
Okay.
Oh, I see. It's pretty much 2.
Yes.
You guys got this one?
Yeah.
Have you gone over, how you know the order?
Oh, let's see. See, that's what keeps killing me.
Yeah, okay. Everybody talked about what the next review with you yet? I did that discussion.
I was on Friday.
Not this week. It ends up that in general,
So that makes
the
more sense.
lower you with the electronegativity, the earlier it goes to the formula. All right, so now, last 15 minutes, I need to touch up a few things or introduce a few things in Chapter 6 that I don't do in the discussion. What we're going to do in the discussion, basically, I'm going to talk about electronegativities, how you use electronegativities, differences in electronegativities to determine, to predict whether or not a bond between 2 atoms in a compound is going to be what we call non-polar, covalent, polar, covalent, or ionic. And I'm going to show you how to draw Lewis structures for compounds. And then, what else do we do? We're not going to do polarities of compounds yet. So if you're looking at the lab, I'm just not going to have you guys fill that part out for anything that's more than diatomic. And the reason for that is we have to talk about geometry of molecules first. That's in Chapter 7. And I'll show you how to predict hybridization. But again, that doesn't come till chapter, I think that's 7 or 8. So, but, okay, a few things in here. First I want to talk about types of covalent bonds.
Give me my apple go. Give me my apple go. Abs.
Abs? Workout? Okay. Apple workout? I didn't know that. I almost started out at 12:30, 11.
I left at like 10 minutes into the lab.
When we start out, when we first talk about covalent bonds with you guys in chemistry, we simply say that 2 atoms come together and they share electrons between the 2, and so as to satisfy the octet rule. And I have given you guys the octet rule here, have I not? Yes. So for example, real simple, if you were to bring, if you had monatomic hydrogen, the Lewis symbol for that is just hydrogen with one valence, with one electron, right?
Mm-hmm.
Bring two of these guys together. In order to satisfy the octet rule, hydrogen wants to be like helium, two valence electrons. So neither one of these, they're just same. They don't have the ability to remove the electron from the other one, so they share, as we say.
The hell?
So both electrons are right between the two atoms. And each of the atoms has its octet rule satisfied. This hydrogen atom sees two valence electrons. This hydrogen atom sees two. So they share. We don't usually write the dots between the atoms. We write them as a line. One line equals two dots. Two electrons here. We have the types of bonds. The only types of covalent bonds you guys will see are single, double, and triple. A single bond is a single line. It's just two electrons shared. A double bond is four electrons shared, two lines. A triple bond is three lines, six electrons shared. Yeah. Example there, so that's a single bond. Double bond, right, look like this. Actually, no, we just.
God.
Double bond. Nice triple bond, an example would be nitrogen. We'll talk more about where these electrons are later when we talk about hydrogen. So, the other thing I want to talk about here is dipole moment, percent ionic character. Dipole moment, I'll write it down.
Doesn't matter where the link is.
Oh, and the Lewis structure of this? Here, here.
5 valence electron can be used for nitrogen. Then it would be keep one, but then it's
Oh,
unequal.
before I do that,
Perfect. Sounds like charge right there.
there's some relationships that are good to know, have in your mind. As long as we have the same two elements on each side of a bond, we know that a single bond is longer than a double bond, which is longer than a triple bond. So the shortest is a triple, the longest is a single. You know what I mean by that in green? Like, so we can say that if we're talking about bond between, I don't know, a carbon and a nitrogen, you know that a carbon-nitrogen single bond is longer than the carbon-nitrogen double bond, which is longer than the carbon-nitrogen triple bond. But now if we talk about, we throw a carbon-hydrogen single bond in there, that might be shorter than a carbon-nitrogen double bond. So you have to be talking about the same elements. The other thing is, the shorter a bond is, in general, the stronger it is, which means the harder it is to break.
Get what?
Somebody close to me heard Purdue, like, what the hell are you writing?
So we predict that a carbon-nitrogen triple bond is not only shorter than a carbon-nitrogen double bond, but it's also stronger than a carbon-nitrogen double bond.
When you say it's harder to break, is it easier for it to shift electrons still, or what do you mean by harder to break it?
Pull those, dissociate these two atoms from each other.
Okay.
Tell us more about that.
Example.
How do you example that, bro?
Give example. Give a little structure.
Here,
So I'll do electronegativity in the discussion.
you're pulling it up.
We're done.
Dipole.
That's not one of his movies.
Sounds like it, right?
It does. Hell, it sounded like it. You had me thinking there for a minute. What the hell is that formula? I don't think I never learned this concept.
It sounds like a spin kick. Yes, yeah, it's like a spin kick. Wait, Hippo is the one that kicks, right?
Yeah.
Yeah, okay, cool.
Hitmo-chan is
He's the one that thunders.
yeah, and then
Okay.
Hitmo-top is the stupid top guy.
It ends up, like I said, I'll talk, if
I
you
don't
haven't
remember
had
the top one at
discussion
all.
yet, I haven't talked about
I
it.
have no memory of the top one.
But it ends up that different elements, when they're bonded to another element, have different strengths with which they pull those electrons in that bond. So a carbon is bonded to a nitrogen. It ends up that nitrogen has a stronger pull on those electrons in that bond than the carbon does. If a hydrogen is bonded to a fluorine. And we'll talk about, when we talk about electronegativity, we'll talk a little more about this. But it ends up that fluorine has a stronger pull on those two electrons in this bond than hydrogen does. And what that means is that these two electrons are shifted over to this side, giving fluorine partial negative charge, giving the partial positive charge on hydrogen. This is supposed to be a lowercase delta, so it's a part of a charge. And we know that these molecules are electrically neutral, and what that means is that the magnitude of these charges has to be the same as each other, just opposite signs.
So kind of the same thing with water.
Yeah, it's a polar molecule, but there's two bonds we have to talk about now in chapter 7. So the thing is, when we're talking about the magnitude of the charge here, we know that the magnitude of these are the same. We're talking about, what the size of that charge is. That's the Q. R is just the distance between the center of this nucleus and the center of this nucleus. Throw those in there, multiply them together, throw the cross product into the calculus. And that gives us what's called the dipole moment.
Magnitude of charge is a number, it's a vector. How do you cross, a number with a vector?
What do you
Well-
magnitude? It's the amount of energy of charge and the distance.
Okay, score 100.
Distance between
But-
charges. Oh! You did it like a 0.
Yeah, and that is exactly right, for sure. Anyway, back to this. Units, okay?
He's so cool.
common unit for chemists anyway, of charge is coulombs and the distance meters. So we get coulomb meters. But the common way to report dipole moments is in this unit called divides. Simple as D. It's 3.336 times 10 to the minus.
Is that 1D?
30. You should know this conversion.
Damn it.
That's something new, huh?
Mm-hmm.
We never learned this.
I don't have this in memory.
I don't have to.
But the first number looks very familiar. The 3.336
Nope.
times 10 to the 30. Yeah, it looks familiar.
What I'll do is, on Tuesday, it'll take me maybe 10 minutes to calculate a dipole moment, calculate a percent ionic character, then we'll go on to chapter 7. So again, make sure that you come to the discussion in lab this week, because that's where you're going to get your